Hi folks, this is Murphy here for Honors Geometry, doing section 2.5, Reasoning with Algebra. This section is kind of an introduction to us being able to justify formally why we can do some of the things that we can do in math. It's a good lead into the concept of proofs because it's something that we're very familiar with, at least I would assume that we're familiar with, being in Honors Geometry, regarding algebra. So we're going to take this concept that we're already familiar with and then apply it in new ways for the purpose of kind of articulating our logic. So let's first kind of put names to some of the properties that are super obvious that I know that you know. And these properties are called equality properties. And they're names for rules that we've always followed. So for instance, there's something called the addition property of equality, which is to say, if I have two values, A and B, that are equal to each other, and a third value, C, well, if I have A and I add C to it, it is also the case that if I take this equation and add C to B as well, then the two quantities stay equal. More or less, if I have two numbers that are equal, if I add C to both, then both of those quantities still stay equal. Basically, I can add C to both sides of an equation. We know how that works. There's also the subtraction property, which works the same way. If I have the equation A equals B, I could subtract C from each side, and the equation still maintains its equality. I could do the same thing with multiplication. I could multiply both sides of the equation by C. And then with division, I could do the same thing, except for one case. There's one instance where if I have the equation A equals B, and I divide by C on both sides, things don't end up being equal. Things end up being undefined. And that's when C equals 0. So we can say the division property of equality works every time, except when you divide by 0, which I'm sure you folks knew. The substitution property, you know what this is. We can just kind of put it in words. If A is equal to B, notice that this is phrased as an if-then sort of statement too, like we were talking about in the previous sections with conditionals. If A equals B, then A can be substituted for B in any equation, and vice versa. You know that that's how substitution works. On the next page is some more equality properties that maybe you don't know by name, but you'd be surprised when they pop up and how often we have to use them for justification for logical deduction. So one is the reflexive property, and it says that for any numbers A and B and C, A is always going to be equal to itself, obviously. So we might see this like when we're done checking our work or something and we get something like 7 equals 7, and we're like, yep, must have done it correctly. But again, you'd be surprised how many times this might pop up in a situation that you didn't expect it to, because it's useful to note that something is equal to itself. There's something called the symmetric property, which if you understand how symmetry works, then it becomes clear why it's named what it is. If A equals B, then it is also the case that B equals A. Sometimes we do this without really noting it. We might flop an equation once we're done solving for x in order to ensure that the variable is on the left side, just because that's our go-to way of presenting it. There's something called the something called the transitive property, which goes as follows. If A equals B and B equals C, then blank. So again, first of all, notice the if-then forms of these conditional statements. And then try to think of this as an example. Like, if I have as much money in my pocket as, like, Jimmy, and Jimmy has as much money in his pocket as, like, Darren, well, then what can we say about the amount of money that I have in my pocket compared to Darren? It's the same thing, because it's both equal to Jimmy. So if A and C are both equal to B, then they're equal to each other. If A is B and B is C, then A is also C. So we might apply this kind of indirectly, especially if there's multiple variables going on. Again, we'll probably use it for logical deduction down the road, and you probably use it in your brain in a non-math context pretty often too. And then the distributive property, I'm sure you know how this works as well. If I'm multiplying A by a quantity, then I would multiply every term inside that quantity by A, and this would eliminate the parentheses. So you can see an algebra example like this where we might try to clean things up a bit via distributing a term to a binomial. So if I distribute to a binomial, by the way, a two-term thing, I'm still going to end up with two terms at the end, assuming that they couldn't have been combined in the first place. Then they won't be able to be combined at the end either. Yay, algebra. Speaking of yay, here's going to be our first proof. So again, the whole notion of a proof is that we are able to show that we're starting with something and then show how we get to our end conclusion by justifying every step of the way, such that if somebody asks why we're doing something or why this or why that, the answers are very clear and very articulated every step of the way. So first, let's solve this straightforward. Let's say we're starting with this equation, And then from here, you can imagine how you would solve this. I'm going to take a wild guess and say that the next thing you would do is subtract 3 from each side. And when you do that, you get here. From here, I bet most of you would decide to distribute. But I'm going to say I can actually do this problem a little bit more quickly by dividing each side by 2. If I do that, then I get x minus 11 equals 5. And then you add 11 to each side and you get x equals 16. Cool. So imagine now that there's an annoying kid in the room that doesn't understand math, and he keeps asking why. Why this? Why that? Why is x equal to 16? And then you would say how the previous step got us from there to this fourth step. But they might ask how you got to the third step then. So then you'd have to justify all the way back to the very beginning here where they ask why this is true. And your justification for why this is true is that this is what the problem told us. It says, given that this is our starting equation, then we can go from there. So kind of like the notion of a postulate, which is just a thing that we assume to be true so that we have something to work off of. Algebra problems and sometimes geometry problems work the same way, where there's just some bit of given information that we have to roll with in order to be able to do anything at all. So for the first step, and usually the first step is going to be something is given to us, and then we have to work from there in order to deduce what follows. So how do we deduce this next step? How do we go from line 1 to line 2? This is the thing that's going to be our justification box for the second line here. How do I go from line 1 to line 2? Well, it looks like what I did is I subtracted 3 from each side. What is the thing that says I'm allowed to subtract 3 from each side of an equation, and then it still maintains its equality? That is called the subtraction property of equality, which we can just call the subtraction property, whatever. From here, again, you may have done this differently. You may have distributed first, in which case you'd end up with 2x minus 22 equals 10, and then you would cite the distributive property, and that's fine. But remember that what I did is I divided each side by 2. So dividing each side by 2 nets the third line for us, so I can cite the division property as a justification for how the third line is true, coming from the previous line. And then from here, I'm hoping you can figure this one out in your head. Not just that I added 11 to each side, but that I should be filling in this last box with the addition property. So note that each line here justifies how we know that the thing to the left of it is true, and how we came from, typically, the step above it to get to it. So sometimes proofs won't be exactly linear like this, where everything comes from the last step. Some things might be like a compilation of previous steps that have come together, but in terms of strictly algebra, especially one variable linear algebra, this is how it's going to go sometimes. So one more example. I would recommend pausing this and then trying it on your own. Not that the solving part's going to be hard, even though sometimes when I throw fractions in there, it ends up being difficult for people, but the justification part, see if you can nail that down. But anyway, again, pause it if you want to. I'm going to proceed. I know this is true. Annoying kid in the room says, after I fill this in, why? Why is that true? And I tell the kid because it's given to us, because that's what the problem literally states. We need some problem to work with, and this is the problem that we're given. From here, I'm sure what you probably did is you added 14 to each side. And once you add 14 to each side, you end up getting the second box, or rather the first box in the second row. And since we added 14 to get here, we cite the addition property as our justification for why this is true. From here, you probably multiplied each side by 3. That would be the multiplication property, obviously. Remember that when you're multiplying fractions, you can kind of think of it like cross simplification, where the 3 in the numerator cancels with the 3 in the denominator. And whenever we multiply a fraction by its denominator, all we're left with is the numerator. I'm hoping this isn't the first time you've heard that, but just a casual reminder. And then from here, I would subtract 4 from each side. Again, there's multiple ways you could do this, but if you subtract 4 from each side, you end up with negative g equals 29, which is almost there. And then from here, I could either multiply by -1 or divide by -1. Whatever, we end up getting the same thing, that g equals negative 29. So you could have done this differently if you wanted. Like from here, I'm just going to show an alternate pathway to solving this problem. From here, I could have added g to each side. If I'd added g to each side instead, then I'd end up with 4 equals 33 plus g. And that would still be the addition property. I could subtract 33 from each side. So according to the subtraction property, if I subtract 33 from each side, I'm left with negative 29 equals g, which is basically it. But then just to show off a new thing of ours, if I want the variable to be nice and tidy on the left, and say I know negative 29 equals g, but therefore g equals negative 29, The thing to cite for that would again be, remember, the symmetric property. The symmetric property is the thing that says if A equals B, then B also equals A. Essentially, if the left side equals the right side in an equation, I can flop the two sides. Say the right side also equals the left side. It's just a good use for cleaning this up and making sure that the variable's on the right. Not always totally necessary, but I just want to show off this property nonetheless. So that was our algebra proofs. I'm dipping into 2.6 a little bit here just to give you an idea of what to expect for the future. Because when we try to use the same logic and justification and steps for geometry, we're not just looking at this in algebra world where there's, addition, subtraction, multiplication, division, and then the other things, substitution, distribution, and then the weird new ones, which may not be new to you, but reflexive, symmetric, transitive, that whole thing. If we're talking about these numbers and these measurements in a geometric context, then we can also cite some other things to demonstrate how we would end up getting the answer here. I have no doubt that if I tell you that ray LM is an angle bisector, then you know to set first of all, you know that these two angles are congruent. Therefore, you know to set the measures equal. So 2t plus 40 equals 4t, and then you solve for t, right? And you eventually get 20. I know you know that. But if we are to articulate why every step of this ends up making sense, or how we know every step of this is true, then we have to go a little bit deep into our set of geometric knowledge here, and this might include properties and postulates and formulas and theorems and definitions as well. So here I kind of filled out what our steps might look like here. We might start with the notion that LM bisects angle KLN, because we're told so, that's our given. Based on that, based on what we know bisection to mean, here is where we can say that this angle on the right, MLN, this guy, is going to be congruent to, maybe I'll stay color-coded here. I think magenta is the closest I have to purple. We know that this MLN is going to be equal to MLK. Think about how we know that based on the previous line. We also know that based on the diagram telling us that MLN is 4t, and then KLM is 2t plus 40, and then from here we can say, therefore, I'm trying to get a new color here. Therefore, we know that this 4t is going to be equal to this 2t plus 40. Then we go from the fourth line here to the fifth via algebra, and then again to the last line via algebra. So think about the steps we would fill in for the justifications. If you want to pause for a minute and actually think this through, that'd be cool, but I'm just going to run through it right now. We know the first line is true because this is given information. It was straight up provided to us at the beginning of the problem. Next, we know that MLN is equal to KLM. In other words, this green is congruent to this magenta, and their measures are equal. Well, we know that that comes from the previous line because that's what it means to be bisected. If we're told that this ray is an angle bisector, then bisection implies that the two parts that it makes are going to be the same. So we would cite the definition of bisection as our reasoning for why this green angle and this purple angle are equal to each other, or their measures are equal to each other. So let's break out of that for a second and note the following. We know that MLN is equal to 4t, and we know that KLM is equal to 2t plus 40 because it's provided in the diagram. So I could write provided in the diagram, but that's basically given information too. It wasn't spelled out in words, it was spelled out visually via the geometric diagram that was provided to us. So there's a lot of given information here that ends up converging. Like, we're given that we have a bisector, we're given that these things are these measures. If I take these two facts and put them together now, and notice how I color-coded too, because I'm such a nice guy. If I take this equation that these two angles are equal to each other, but then also that these two angles have these measurements in terms of t, what I could end up doing is taking this 4t that MLN is equal to, and plugging it into the green side of this equation, the left side. This is getting a bit sloppy here, but I want you to see what I've done basically. I've taken this green equation, and I've substituted some parts. I put 4t in for green. This 2t plus 40, which is equal to the purple, if I plug that in there, then I end up with this next line, 4t equals 2t plus 40. This is all the stuff that we don't really, like, yeah, I know you do this in your head. I know you do this in your head in a couple seconds too, but what we've essentially done is we've acknowledged that if the angle measures are equal, then we can write those angle measures in terms of t via substitution. So the substitution property is what allows me to go from talking about these in the abstract form of the measure of angle whatever, to straight up talking about them in terms of degrees and t values. So then from here, how do I get from 4t equals 2t plus 40 to the next line? It sure does look like I just subtracted 2t. And now we're back in algebra world, where we can say that that's the subtraction property. And then to get from the second to the last line, you divide by 2, which, yes, student, that is the division property. So here's a problem that I'm going to give you, maybe just to think about. This one's a little bit trickier, but I would recommend the first thing you do be to convince yourself that this is true. That if segment AB is congruent to segment CD, or in other words, if their lengths are the same, or if they have the same measure, how can we therefore conclude that segment AC is equal to segment BD in terms of measure? Think this through, and we will talk about it next time I see you.